Welcome back to Programming Fluency. This is section 9.3, Command Line Arguments. So far, every input has been hard-coded into your source. Want a different file? Edit the code and recompile. In this video, you will let the user pass file names and options right on the command line. Let's begin. Every program you have written so far has its inputs hard-coded, but real tools do not work that way. When you type gcc-wall-oh hello.c, the compiler reads those file names from the command line. Let's learn how your own programs can do the same. This is the plan for this video. First, argc and argv, this is how main receives what the user typed. Next, the argv array, string pointers where argv0 is the program name and the array ends in null. Then turning arguments into numbers, a to I the simple way and strtol the safe way. After that, usage messages. You tell the user how to run your program. Finally, option flags. You parse -v and -n by looping over argv. Until now, you wrote main with no parameters, int main void. But there is a second form of main that receives what the user typed on the command line. It is int main, int argc, *argv square brackets. Every Unix tool you have ever used takes this form. GCC, ls, cat, cp, they all read their file names and options from command line arguments, instead of having them hard-coded. Let's see exactly what these two parameters hold. Suppose you run /args, then hello, world, and 42. argc is the argument count, and it includes the program name itself, so here argc is 4. argz is the argument vector, an array of strings, one per word on the command line. argv0 is always the program name. So argv0 is /args, argv1 is hello, argv2 is world, and argv3 is the string 42. Notice that last one. It is the string 42, not the integer 42. Every command line argument arrives as a string. This is how you walk through the arguments. It is the classic first program. We print argc, the count. Then a for loop runs I from 0 up to argc-1, printing each argv element as a string. One thing to watch closely. The loop condition is I less than argc, not less than or equal. If you wrote I less than or equal to argc, you would read argv at index argc. That slot is not out of bounds. It is the standard null sentinel that always sits at the end of argv. The bug is that you would then pass that null pointer to %s, which is undefined behavior. So always loop with I less than argc. This figure shows the layout in memory. Here argc is 4, so there are 4 real entries. argv is an array of ** pointers. Each pointer leads to its own null terminated string on the right. argv1 points to hello, argv2 to world, and argv3 to the string 42. argv0 points to the program name, /args. And there is one more slot. argv at index argc, that is argv4 here, holds null, marking the end of the array. You usually use argc to control your loop, rather than checking for the null. Since every argument is a string, if you need a number you have to convert it. The user passes 42, and you receive the string 42, 2 characters plus a null terminator, not the value 42. The simplest converter is a to I, ASCII to integer, from standard library.ha to I of the string 42 returns the integer 42. But a to I has a dangerous flaw. It cannot report errors. A to I of the string a BC silently returns 0, and if the number is too big for an int, the behavior is undefined. You cannot tell a real 0 from a broken input. The safe alternative is strtol, string to long. It reports where parsing stopped and it detects overflow. First we set errno to 0. Errno is a global flag that the library sets when a call fails. You will learn it fully in the next video. For now, just 0 it, then check it for overflow. Then we call strtol with the string, the address of an end pointer and the base, 10 for decimal. Now 3 checks. First, if the end pointer equals argv1, no digits were parsed at all, so it is not a number. Second, if the character at the end pointer is not the null terminator, there is trailing junk after the number. Third, if errno equals erange, the value overflowed. Together these catch every kind of bad input. For any program that handles real user input, use strtol. When the user runs your program with the wrong arguments, they need to know how to fix it. That is what a usage message is for. If argc is not 3, we print usage, then the program name, then the expected arguments in angle brackets, and we return 1. 3 conventions here. First, print the usage message to standard error, not standard out, because it is an error, not normal output. Second, use argv0 for the program name, so the message stays correct even if the user renamed the executable. Third, return a non-zero exit code, usually 1, so a shell script knows the program did not succeed. Let's put it together in a real utility that sums any number of integer arguments. The loop starts at I equals 1, skipping argv0, the program name. For each argument, we first set errno to 0, then call strtol to parse it. Then we validate 3 ways. If end equals argvi, there were no digits at all. If the character at end is not the null terminator, there is trailing junk. And if errno is erange, the number overflowed. Any of these means the argument was not a clean number, so we report it and quit. Next, before adding, we check that the running total itself will not overflow along. Only then do we add the value. At the end, we print the sum. This shows the everyday pattern. Loop from 1 to argc-1, convert each argument safely, and use it. Notice the total is a long, matching what strtol returns. Many tools accept flags, short arguments that modify behavior, like ls-l or ls-. You implement them by looping through argv and checking each argument. If the argument is -v, we set the verbose flag. If it is -n, then the next argument is its value, so we check that a next argument exists, then advance I to consume it. If the argument starts with a dash but we do not recognize it, we report an unknown option. Otherwise, it is a positional argument like the file name. The check I plus 1 less than argc stops you from reading past the end. Now the common mistakes. The first is accessing argv without checking argc. Here we grab argv1 as the file name with no check. But if the user runs the program with no arguments, argc is 1 and argv1 is null. Passing null to fopen is undefined behavior, and it usually crashes. The fix is to check argc before you touch argv if argc is less than 2. Print a usage message and return. Always confirm the argument exists before you read it. The second mistake is trusting a to I on user input. Here we convert argv1 with a to I and use the result as an allocation size. But if the user passes a BC, a to I returns 0 silently, so malloc of 0 gives you nothing usable. and if the user passes a negative number as a string, n becomes negative, and n times size of int wraps around to a giant unsigned value, because malloc takes an unsigned size. The fix is to use strtol with proper error checks, or, at the very least, validate the result. If n is less than or equal to 0, reject it before you allocate. Let's recap. Main can receive command line arguments through int argc and *argv. argc is the count, including the program name, and argv0 is that name. The user's own arguments start at argv1, and argv at index argc is always null. Every argument is a string, so convert it with a to I for a quick job, or strtol for robust code with error checking. Usage messages go to standard error. Use argv0 for the program name, and return a non-zero exit code. And you parse option flags by looping through argv and comparing each argument with strcmp. Next, your programs read files and take arguments. But what happens when a file is missing or the disk fills up? In the next video, you will learn C's error handling, error, p error, str error, and the cleanup patterns that go with them.